Okay, so we are starting 4.2 discontinuities of rational functions. These are going to be our notes. Hopefully we'll get through them all. If not, we will continue and complete them tomorrow. Your assignment for 4.2 is going to be part of your assignment with 4.3, okay? So it's not going to be its own assignment. It's going to be combined with 4.3. All right, so we're going to do a quick review of what we talked about yesterday. Is that cool? Either way, it's happening. So first off, we have f of x equals 1 over x minus 2. And we know that this is a, what kind of function? It's a rational function. Why is it a rational function? There's a variable in the denominator, right? The polynomial is in the denominator, okay? So when we talked about this yesterday, we determined that because this is x minus 2, right? That means that our rational function was shifted to the what? To the right, because our x's are what? Liars. So that means that this is our parent function shifted to the right, okay? And we also talked about that. That is our, my pen stopped working. My pen stopped working. Oh gosh, there. What? Oh, it stopped working though. So this was a shift to the right, okay? And because of that, that meant that our vertical asymptote also shifted, correct? So because our vertical asymptote shifted, what is the domain of this rational function? Or 2 to infinity, right? That's kind of what we talked about yesterday. Agreed? Okay. Okay. What we're going to talk about today is what's happening around your 2. So what's happening as you get close to 2? Okay. So first we're going to look at a table as x is going to 2 from the left, and then we're going to look at the table as x is going to 2 from the right. Okay. So coming from the left, we're going to start at 1 and make our way towards 2. Coming from the right, we're going to start at 3 and make our way towards 2. Now, what I'm going to do is I'm going to use my calculator. You don't have to use one, but if you want to follow along, you can. I'm going to pull up the graph. Let me reset mine. Second plus 7, 1, 2. Okay. So I'm going to go to y equals, and I'm going to put in 1 divided by x minus 2. Okay. I want to be able to make my own table. Does anyone remember how to make your own table on the calculator? What do I need to do? I want to be able to put my own values. It's actually second window before I go to second graph. And that's because I want to go from being a auto table to an AS table. What this is going to allow me to do is fill in the values that I want or need. Okay. So I need 1, so I can type in 1. And what's my value for 1? -1. I need 1.5. And I'm going to get -2. I need 1 and 9/10. I need 1 and 99 hundredths. And I need 1 and 99 thousandths. Okay. So now I can fill in those values. As we're looking at these values, if I kept going and the closer and closer I get to 2, what is happening to the y values? They're decreasing really fast. They're decreasing. So if I'm forever decreasing, what am I heading towards? Negative infinity. So we had -1, -2, -10, -100, and -1000. If this was to keep going, so if I was at 1.99999999999, it just keeps going and keep going. And so what are my x values doing? They're approaching negative infinity. Okay. So as I'm in the middle of teaching. Okay. So coming from the left is going to be doing this. So what I see here, it's saying coming from the left, it's going to be like, right? Okay. Now let's talk about 3. So I'm going to do the same thing that we did with the left side on the right side of 2. Let me pull out my handy dandy calculator. Oh, that's not a calculator. I can't. Thank you. Because I cannot. All right. So I'm going to put in 3. I'm going to put in 2.5. 2.1. I'm going to put in 2 and 100 and 2 and 1,000. Now, what do you notice is happening with these y values? It's opposite. It's increasing very rapidly, right? So now we have +1, +2, 10, 100, and 1,000. So what's happening coming from the right? What's happening to my y values? They're heading towards positive infinity. So coming from the right, my graph is doing this. Growing exponentially, right? Okay, so now we're going to put it together. So on the bottom, we're going to create a graph of 1 over x minus 2. Okay? So creating our graph is this sketch f of x near x equals 2. So the first thing we have is that there's some type of boundary, right? Because did either value ever get close to 2? Do you think it is? Yeah. So if I type in 2, what should happen? We get nothing. We get an error. It's undefined. There's no value there. So that's why that's our boundary line. Do you see that? Okay. The other thing we talked about yesterday, what else do I know that there is? What is my other discontinuity happening here? From graphing yesterday. So we have 1 over x minus 2. And that where's that horizontal asymptote at? It's going to be at 0. Because there's nothing being added or subtracted. Sure. Okay. So we said coming from the right. So starting at 1, what was the value of 1? Huh? On our table?
Value of 1 or
-1. So at 1, it's at -1. So somewhere in here, right? Then we were at 1.5, and it was at -2. And then it keeps going, and it's starting to do what? It just starts going faster. So it's going. Okay. Okay. Then on the left side, so with our guys, on on the right side, we have starting from 3. What's happening to these values? They're increasing. So at 3, it started going like this. Boop, 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 boop. Yes, but we're writing in terms of the behavior. Okay, so our behavior is as x approaches 2, and we're going to write from the left by putting a negative there. F of x is doing what? F of x approaches negative infinity. So we're describing the behavior of the function. On this side, as x approaches 2 from the right, what is f of x doing? Infinity. Okay. Writing in you're describing behavior of the asymptotes, and in behavior are key things that you need to be able to do for calculus. Okay.
Was that
right? When we start talking about limits.
like M?
All right, continuing. All right. So in conclusion, it says the definition, the line x equals a is a discontinuity. Okay. And the discontinuity that it is, we call it an asymptote. Of f of x, if as x goes to a from the left or right, they're doing different behaviors. So they're not approaching the same value. Because normally when you're graphing at 2, it's a value, right? It's a set value. But if I don't have a value, there's something causing a problem. A discontinuity can be a hole, a gap, or an asymptote in your function. But yes. Yeah. Why isn't there a value there? It's creating some type of error in your graph. Okay. And so in this graph, our error comes because of an asymptote. Okay. So in conclusion here, x equals 2 is a discontinuity of f of x equals 1 over x minus 2. Okay, because it's a error in the function. All right. So further into discontinuities. So discontinuities of rational functions. The graph of the rational function will have a discontinuity at each real root. Okay. So each real root of the denominator. Discontinuities are happening in the denominator. Okay. Now, if x minus c is a factor, is a common factor, then f of x has a hole in the graph, in the function. How do you spell function? There you go. Okay. So if I factor my numerator and my denominator and they have a common factor, that's called a hole in my graph. There's a hole in my graph. Okay. Then it'll be a hole and then continue from there. Yep. All right. So to find the location, thank you, Gael, for acknowledging it. To find location of the hole, evaluate the reduced form of x minus f of x at x equals c. So basically, you're just going to take x minus c and set x minus c and set it equal to 0 to figure out exactly where your hole is, just like any other factor, right? Okay. If x minus c is not a common factor, f of x has a vertical asymptote. All the time.
Wait.
We can. I can't stand your hole. Here we go. All right. F of x equals 2x minus 1 over x plus 4. And it wants us to describe domain and discontinuities. Okay. So the first thing you want to do is make sure that it is factored. You want to make sure that your numerator and denominator are fully factored. Are they fully factored? Yes. They are fully factored. 2x minus 1. Or is there a GCF? No. Is it a trinomial that can be factored? No. Same thing for x plus 4. Yes. But we're not worried about proper format. We're worried about discontinuities right now. Okay. All right. So because they're fully factored and they do not have anything in common, then there is no hole in your graph. Okay. So there's no hole. Huh? They're fully factored and there's no common factor. Like there's not an x plus 4 in the numerator or 2x minus 1 in the denominator. So they have nothing in common. If the whole factor repeats itself, then there is a hole. Okay. All right. Vertical asymptote. Your vertical asymptote comes from your factor and your denominator. What is our factor in our denominator? Our factor is x plus 4. And you set that equal to 0, and that's how your vertical asymptote is determined. So what is our vertical asymptote? X, that's not an x. X equals -4. Okay. These two create your domain. I only have one discontinuity and it's at x equals -4. So my domain is from -infinity to -4 or -4 to infinity. I'm going to show you next. You identify your discontinuities first in order to write your domain. Okay. All right. 6. So again, you want to check it. Is the numerator and denominator fully factored? No, they're not. So your numerator can be factored by difference of 2 squares. Okay. So difference of 2 squares means I take the square root of x squared, which is x, the square root of 9, which is, and when you take the square root of something, it's going to produce a negative and a positive. So that is the factor of x squared minus 9. How do I factor the denominator? I ask myself what? It's exactly what multiplies to give me -6, but adds to give me 1. It would be a +3 and a -2, right? 3 times -2 is -6. 3 minus 2 is 1. Do we see that? Okay, so now, do I have a common factor in the numerator and the denominator? Yes. So I'm going to circle that because that's where my hole is. My hole is at where they have a common factor. So I have a hole at x plus 3 equals 0. So where is my hole located at? X equals -3. Okay? My vertical asymptote is whatever is left in the denominator. What is left in the denominator? X minus 2. So x minus 2 equal to 0 is my vertical asymptote. So where is my vertical asymptote at? X equal 2. These two values are my discontinuities of my domain. And I have to write them all the way. I'm going to tell you, I tried to make your box bigger, but you're probably going to write like diagonally. So here we go. We have negative infinity. Out of these two discontinuities, which one will I hit first? -3. So I'm traveling along, minding my own business. Oh no, there's a hole in my graph. So then I have to stop. And then I go from -3 to 2 because, oh no, there's an asymptote. So I stop and then I continue to infinity. And that is my complete domain in interval notation. Exactly. Okay, so the graph looks like this. On the older calculators, it's not going to be very clear, but we'll do our best. Because you cannot use Desmos in calculus, and so therefore I cannot get you used to using Desmos. It is not allowed to be utilized on the AP calculus test. So it's okay. I can show you. You're in a what class though? Didn't we have a discussion on what the purpose of pre-AP is? Oh, okay. All right, so notice the graph is going and then it, okay. Okay, so you really can't see the -3, but if we go to the table and we go to, oh, I need to turn my table back to auto. It's okay, I can fix that. But notice when I go to -3, what does it say? Error. That's because if I was able to zoom in at -3, I would be able to see it. Now, my old school calculator, good old faithful here. Software? Because this is what I've been using since 8th grade and it makes me feel better. Yeah. Okay. So when I trace, so notice how as I'm tracing, it just jumps over -3. If I type in -3, look, what does it say? There's nothing there. Do you notice how Y is empty when I type in -3? Right. I trace and I type in -3. Notice how it says, oh, there's nothing there. Why? Because there's a hole in the graph. Okay. No, it's like literally right after this point. It's in between here and here. You can't see it. I just told you, you're not going to be able to see it because the calculator doesn't have that ability to show you exactly from here. Okay. And zoom in at -3. It's a hole in the graph. It's literally a gap in the graph where everything else works around it, but not at that point. I felt more accepting of this as a student, and you guys were like,
it works. Be right here.
yes, exactly.
After factoring this out,
Here we go. So on 7, we have f of x equals 5 over x squared plus 1. Okay. So this one, Does it have a common factor? Does it have a common factor? No. So do we have any holes? No. There are no common factors, so therefore there are no holes. Okay? Now, your vertical asymptote. So the thing here is if I was to take x squared plus 1 and set it equal to 0, I end up with x squared equals -1. So x equals plus or minus I. Can you have imaginary boundary lines? No. An asymptote is just one imaginary. Can I have imaginary boundary lines? So guess what that means? There are no vertical asymptotes. And because there's no discontinuities, that means that my domain is all real numbers. It goes from negative infinity to positive infinity. Okay? So let's look at the graph of that. I'm going to go to my... So I'm going to go graph 5 divided by x squared plus 1. And I hit graph. And notice that there is not a vertical asymptote. If I go look at my table, every value is defined. There's no errors that are occurring. Okay, and that's again because when I set what was equal in the denominator equal to 0, yes. When you set it equal to 0, we end up with imaginary values. So it's all real numbers. Okay. All right, 8. So 8 is our last example for this, for holes and asymptotes, vertical asymptotes. If I was to factor this, remember this is factoring with the what method? Xbox. You can Xbox, you can quadratic formula, but you're asking yourself what multiplies to give you -30, but adds to give you -7. Okay. Multiplies to give me -30, but adds to give me -7. 3 and -10. So if I went into Xbox mode, we have 6x squared, we have -5, and we have 3x and -10x. The GCF between 6x squared and -10x is 2x. The GCF between 3x and -5 is 1. GCF between 6x squared and 3x is 3x. The GCF between -10 and -5 is -5. Toodles. So therefore, my factors of the denominator are those. I'm going to write it down here. We have 2x plus 1 times 3x minus 5. I did it. All right, so notice here that once we are fully factored, it doesn't appear that they're the same. However, here, if I factor out -1, so if I factor out -1, I would be left with 3x minus 5. So now I do have a common factor, and my common factor is 3x minus 5. 3x minus 5. So this is where my hole is in my graph. So I would take 3x minus 5, set it equal to 0, and therefore I have x equals 5 divided by 3. Okay? Then whatever is left in the denominator is where my vertical asymptote is. So what's left in the denominator is 2x plus 1. So I have 2x plus 1 equals 0. So we have x equals -1 divided by 2 is my vertical asymptote. Okay? So now when I write my domain, it goes from -infinity to -1/2. -1/2 is smaller than 5/3. Or from -1/2 to 5/3. Or 5/3 to infinity. Okay. 5/3 to infinity. So that's my full domain in interval notation. Okay, so that is vertical asymptotes and holes. And tomorrow we will continue with horizontal asymptotes and slant asymptotes.